Hello everyone, welcome back to another video where today we're going to be tackling a material energy balance problem, okay? And up top is our problem statement, and it's saying we have a CSTR, continuous stirred reactor, that can exhibit nonlinear dynamic behavior. We simulate a step of change in coolant temperature in positive and negative direction. So what that's telling us that we're going to be using some differential equations to simulate our reactor, okay? And down here in the table is all of our different initial conditions, okay? Q, flow rate, and before I ramble through everything, you can pretty much tell what each parameter is by looking at its units. CAI, well, it's given in multiple liters, so C is concentration, as opposed to C, capital C, where it's given in joules over grams times Kelvin. Obviously, that's not concentration. What does that look like? That looks like our specific heat unit. C is specific heat. So that's what we're going to throw into our Python. So moving over to the iPad, what we see, well, what I'm illustrating right now is, okay, we have a, if you'll excuse me, we have a reactor that is exhibiting a first order reaction where our concentration of interest A reacts to the first order to produce a product B, which we're not concerned about B. What we're concerned about is the rate at which A disappears and enters the tank. I forgot to mention that A enters the tank, CA in, and the mixture exits the tank too. And once again, we have another well-stirred problem. What that tells us is that the concentration out is equivalent to the concentration of the tank. So CA is going out, okay? And you're looking at this, this looks a little bit different. What's that jacket around the reactor? The jacket is a cooling jacket, okay? It's a cooling jacket. So what that coolant jacket is coolant goes in at a certain temperature, C, T, C, I, and coolant exits at a slightly higher temperature, because we also know that this reaction is an exothermic reaction, so the coolant takes away some amount of enthalpy, some amount of heat away from the reaction. TC out. Okay? That is our problem statement. Okay, so moving on, we see on the screen right now, I already have up, is the Arrhenius equation, which you've probably seen in your general chemistry 2 course. And the reason why I want to start with this is that if we go over to our initial conditions, we see that we've given a parameter E over R. It's not a very common parameter. Well, it might be in chemical engineering, but I don't know yet. It's not something I've seen before, okay? But what we notice is in the Arrhenius equation, what do we have? We have activation energy over R. So don't be fooled by a somewhat odd looking initial condition, because what that is, well, maybe we'll factor it out to make it more clear. We're provided K naught raised to the exponential of, and we are provided E over R times the reciprocal of T. We now have a usable Arrhenius equation. And once again, remember that I described the reaction as a first order reaction. Therefore, the rate of the reaction is equal to K times the concentration of A. Simple as that, right? To the first power, because it's first order, but that's besides the point. So the goal, recall that the goal of this problem is to derive 2 different differential equations to simulate this situation. And what those 2 differential equations are is that one will be focused on the mass balance, okay, mass in, mass out, and the second one is the mass energy balance, where we're still accounting for mass, but we're focused on the enthalpy, the energy. Okay, but we'll start with mass. And what does every mass balance problem start with? Okay, if you're a chemical engineer, you should be reciting this in your sleep at this point. Accumulation equals in minus out And in this case, there's no generation of A, but there is consumption of A. Consumption. Okay? What's accumulation? Accumulation, so we'll call this accumulation as our dependent variable in our differential equation. So what is it? It's dCA over dt with respect to time. But let's analyze these units. It's moles per liter over time. That's not mass. This is a mass balance, right? In order to get it to be a mass balance, we have to multiply by V. Okay, multiply by V. Okay, and let's set up the right-hand side of our differential equation now. What do we have? We have, let's see, we have Q, flow rate, times in and out. I mean, out minus in, right? Out minus, no, sorry, in minus out. In minus out. I'm getting myself mixed up by trying to talk at the same time. It's in minus out. We can see very clearly right here. Okay, so concentration of A going in minus the concentration of A going out. Okay, and then consumption. How do we describe consumption? Well, consumption is the rate, where have we heard that before? The rate at which A is being consumed. Therefore, consumption is very simply a matter of this rate law, K times A. Okay, let's look at the units again, okay? Over here, remember flow rate, it's volumetric flow rate. So it's units of, let me think, volume, so liters over time multiplied by moles per liter. Okay? Over here, right now, we just have K. K is it's our rate. Okay. Let's describe it this way instead so we don't get confused. The rate, we're focused on what this expression is equivalent to. Okay? And it's the volumetric rate. It's not the volumetric rate. Sorry. It's the rate at which A is being consumed. So A is in concentration, so mole per liter times reciprocal time. We're missing a volume in the numerator. So we fixed that very simply by just multiplying by V. Okay? That was kind of a mess, but the end result is there. I apologize for this quick detour. But let's get this in a form where we can plug it into scipy.solve IVP. We have our right-hand side, but our left-hand side is not quite in the desired form yet. We still have that V. How do we get rid of it? It's very simply a matter of dividing by V on both sides, all right? Easy algebra. So we have dCA, the concentration of A over time, derivative concentration of A over time with respect to time, equals Q, volumetric flow rate, times concentration of A going in minus concentration of A going out over volume, specific volume. Okay, notice how here this cancels out. So all we're left with is minus K times let's relabel that. K times the concentration of A. Okay? We're thinking prepping us for Python. So this is what I'm going to call my variable in Python, CA. But when I'm talking to you, I'll call it the concentration of A. Because you can name the variable anything you want. Okay? Oh, we don't divide by anything because V specific volume cancels out. Okay? So what do we have? We now have our first differential equation, which models the mass balance of the reactor. Okay, at this point we're ready to start deriving the second differential equation, which is our mass energy balance. And what I'll want to start with is, notice how I start with the derivative of concentration of A with respect to time. because once I solve this, make Python solve this differential equation, I get an equation that can model the concentration of A as time progressive. What I want to do next is have an equation where I can model the temperature of the reactor as time progresses. So therefore, I start with the derivative of the temperature of the reactor with respect to time. Okay? And it's a mass energy balance, so what the units on the left and right hand side, what I want them to be is in joules. Okay? Total joules. So how do I get from temperature to joules? Well, usually to get from temperature to joules, you use Q equals mc delta T. C, specific heat, so I'll want to multiply by specific heat. But specific heat, because due to the nature of its units, likes to be multiplied by a unit of mass. We're not given a unit of mass. We don't know how much mass is inside of the reactor at a certain time, except we do. We use other pieces of information in order to get there. What do we use? We are given the volume of the reactor, as well as the density of the contents of the reactor. So density times volume is equal to mass. Mass multiplied by C, specific heat multiplied by temperature, equals joules. There we go. We have joules on the left-hand side. On the right-hand side, we have a number of terms. Okay, we have the enthalpy of the contents going in minus the enthalpy of the contents going out minus, I'm going to call this HC for H cooling or H conducting. And what HC is, it's a term which describes the energy transfer by conduction of the walls of the reactor from the contents of the reactor to the coolant jacket. Okay? And finally, this is a positive term. We add the enthalpy of reaction. It's an exothermic reaction, so it's negative, right? And let's start. I got a bit ahead of myself, but let's start replacing these terms with terms that we know and can simulate. Okay? So this is the enthalpy of reaction. What do I multiply it by to get the total energy released by a reaction per unit time? I multiply by rate. We know rate. We have a expression for rate, so therefore I multiply by K times A, right? K times Ca, concentration of A. Let's bring that down. Plus negative delta HR times K times Ca. Okay, let's start with the enthalpy of contents going in and out. What is that? We multiplied by volumetric flow rate multiplied by C. Okay, this is volumetric. We're not dealing with volume here, we're dealing with mass. Therefore, I multiply by density as well, multiplied by the quantity, temperature of the reactants going in, minus, this is where you need to remember the concept of well stirred. Well stirred means that the concentration of things going out is equal to the concentration of the tank. Therefore, the temperature of the things going out is equal to the temperature of the tank. So, T R, simply TR. Okay, let's move this term out a bit. I don't have enough room. Okay, minus H conducting. What do we have? We have, well, normally what you use, we're very, very familiar with Q equals mc delta T. This is a new equation, at least new to me, which is we have a term UA, which is given in joules over minute times Kelvin. What does that look like? It looks like, let's describe it in words. It's describing words. Okay, the rate at which heat is being transferred per unit temperature. So UA, what do we multiply by? Well, we should multiply by the difference between the two temperatures that it's conducting between. The difference being the contents of the reactor, the temperature of the reactor minus the temperature of the coolant. Well, there we go. This left-hand side equals this right-hand side. Okay? And now we sing the same song. We want to get the dependent variable by itself, right? What do? We divide by rho VC. And you'll notice that something cancel out. We'll see. Well, you'll see. So dtr over dt equals, well, rho cancels out. We are left with q, and c cancels out. So we're really just left with q times temperature of the reactants going in minus temperature of the reactor over volume minus I'll call it conduction factor, I suppose. I know there's a real name for it, but I don't know it off the top of my head. Over temperature of the reactor minus the difference between the temperature of the reactor over and the temperature of the coolant, all over rho VC. Nothing cancels here. Rho VC. Here, only does C cancel out? Or am I missing something? I might be missing something. Well, let's write it out anyway. The reaction enthalpy, HR, times rate at which things are reacting. Oh, I see now. If I'm not mistaken, this should be multiplied by rho. I'm not sure. Actually, I'm not sure. I'm not going to make that decision yet. All over rho VC. Okay? Now, I'm looking at this and I know it's wrong. Because if memory serves, something should cancel out. So, there will be an addendum. I can tell that in editing there will be an addendum to this. This is wrong, but there's something supposed to be here or here, and I can't quite deduce out what. So we'll be right back. And we're back. I was missing something. That being volume right here. There should be a volume. So since there's a volume there, all we're left with is rho and C. Okay? The reason why there's a volume there, because let's check the units. We have, let's see. I'm trying to get the right. Okay, we have the rate at which C is reacting. So we have moles. Sorry. We have moles over liters. Okay, multiplied by what unit is delta HR given in? Delta HR is given in joules per moles. Joules per moles. Moles cancels out, but not liters. So we need to multiply by a volume term in order to get everything to just be joules. Therefore, this this is now our final derived expression for the differential equation modeling temperature of the reactants, temperature of the reactor. This is a mass energy balance. So these are our two differential equations, which we will take into Python and code out and get some equations that will model our problem statement. Okay, we'll be right back and meet you in Python. Okay, now that we're in Python, let's start the coding portion of this homework. Okay, and you'll see that right now I have my standard imports. We have numpy as always. And for this problem, we want to numerically solve a differential equation. Therefore, we have scipy.integrate solve IVP, and then we have our plotting imports. And then we see that we have a series of initial conditions and parameters, and those are very simply from oh shoot, I don't have my reference pulled up. Just one moment. Very simply from the problem statement of the homework right here. Okay, so what do we always do when we want to solve a differential equation. We want to define the right-hand side, which takes in time and the independent variables. Okay? And we'll call that vec. Oops. It's almost like if I leave for spring break for 1 week and suddenly I forget how to do Python. Right? And we want to unpack vec as our two independent variables, that being the temperature. Well, we start with actually the concentration of A and the temperature of the reactor, vec. And we want to return an array of our two right-hand sides, that being Q times C concentration of A going in minus concentration of A going out. Since it's well mixed, that's very simply the concentration of A within the reactor divided by volume minus special K, times concentration of A. And you might say, Quan, we're not given K. What is K? What do we do with K? Well, remember from the beginning of our derivations, we pointed out that we are using the Arrhenius equation because we're given K naught and we're given activation energy over R. So, therefore, K is equal to K naught times NP dot exponential ER, actually negative ER, divided by TR. Alright, there we have K defined now. Our second right-hand side is going to be our mass energy equation, the second differential equation that we derived. And that's going to be Q times the temperature of the reactor going in, which here we'll define as Tn, minus the temperature of the reactor, all over volume, minus UA, which is the, what do you call it? I call it the conduction factor, heat transfer conduction factor, something like that. The difference between the temperature of the reactor and the temperature of the coolant, right? All over the quantity, rho times volume times C, capital C. I am fairly certain that I define it as capital C, yes. Plus the heat of reaction times K times concentration of A over the quantity rho times specific heat. Alright, that's our right hand side. We move on to solve the IVP, solve underscore IVP. Okay, which wants our function right hand side, a tuple of the T span, which 0 T end. Our initial conditions, that being CA naught and T naught, method, which in this class we always use Rodot. And we do want dense output because we want the function to be able to intelligently choose what points to evaluate. And I believe that is it. See if solve IVP works. Message, solver successfully reached end of integration interval. Great. So then we can pull the solution function out of this. I won't bore you again with what the solution function does, since I've gone over it many a time in my previous videos. We will then ask it, actually, we first say that we want T for plotting purposes equals np.linspace T end, sorry, 0 T end 1000, something like that, right? Then we say, we want to say that CA and T equals solution t-plot. Alright, then we start plotting. Make by doing, I think it's, no, fig equals make underscore sub plots, right? Man, I haven't done this in a while and I already feel the information decaying. The functions are not coming to my mind as quickly as they normally do. Fig dot, wait. We have two plots, so we do want them to be side by side. So we say that, okay, I want 2 columns and 1 row. I believe that's how you do it, okay? Then you do fig dot add underscore scatter x equals t-plot. If I can type, holy moly. Y equals, we'll make the first one concentration, I suppose. Name equals concentration of A, row, column equals 1, row equals 1, and mode equals lines. All right. That is our first plot. We very simply repeat it and say that, okay, this time I want T, the temperature. And I'm now naming this temperature, or reactor temp, K, in Kelvin. And put this in the second column. So they're side by side. And there we go. Perfect. I'm very happy this worked first try. Alright? Normally doesn't happen. And you'll see that our blue line represents the concentration of A. Alright? And the red line represents reactor temp. And you'll see that initially there's not a lot of A because it's all being consumed. And that's reflected by the temperature. It's very exothermic and you see it's very hot. And as A becomes consumed and we reach a saturation of A, steady state, the temperature then levels out. So recall that the problem statement asks, okay, what happens when we change the cooling temperature from 300 to 290 by increasing the cooling rate by changing the cooling temperature from 300 to 290. See what happens. All right, plug in 290. What happens? All right, we see that the reaction will progress like this and it will reach saturation much earlier than before, and we see that the temperature drops much earlier than before and reaches steady state much earlier. What happens if we decrease the cooling rate? Okay, change this to 305, just a 5-degree difference. Okay, 5-degree difference, and we'll see how amazing that is. Look at that, no steady state. Not to mention that there's a large exotherm, all the way to 440 degrees Kelvin, and then it oscillates and never reaches steady state. And this is a great problem to illustrate how minute changes, change it back to 300, can have such a large impact and it's not immediately obvious, right? It also shows the beauty of using Python to solve this, because this would be a pain in the butt to solve by hand. Make the computer do all the hard math, right? So yeah, now we've illustrated what happens if we increase the cooling rate or decrease the cooling rate, and we have a viable simulation for the reaction of this specific problem statement. Well, with that out of the way, this concludes homework 4, and we'll see you in the next video.